It's all working. Okay, hi everyone. Thanks for coming to this meeting of the Formal Demography Working Group. I'm Monica Alexander. I'm at the University of Toronto and I co-organise this group with Vanessa DeLago, who's at the Vienna Institute of Demography, and Rio, who's at SDU in Denmark. Unfortunately, Rio's daughter is sick today, so he can't be with us. So we're super excited today to have Matt Hauer talk to us. So Matt is an assistant professor in sociology at Florida State University, and his work is far-reaching in demography, but a large focus of his research is the intersection of demographic change and climate change, and in particular how climate change will affect current and future migration patterns. Matt does a whole bunch of really interesting work, and actually one of my favourite methodological papers in demography in recent years, Matt co-authored with Carl Schmertman on, some of you may know it, it's about calculating fertility rates from population age structures. But anyway, today Matt's with us to talk about more the climate side. Thanks very much for agreeing to talk to us today. Super excited, and take it away, Matt. Thanks.
Thanks, that's too kind. So I am going to talk about my work on climate migration, and in particular, sort of the second half of the paper is about multi-regional population projections, which I think this is like a super niche area within demographic methods, because from what I could find, there's very little material online or elsewhere on multi-regional Leslie matrices that haven't at least been published like after 1980 or so. And I'm using these to think about climate migration and in particular demographic change. So I actually, there'll be sort of like, to do this kind of work around climate migration, I have to do two separate analyses. One is around estimating population displacement, and then the second is integrating that into a multi-regional Leslie matrix. So I'm going to talk about both of those, and the first part will be a little bit more statistical, and then I'll relate it, don't worry, I'll relate it directly into demographic methods, and then the second part is much more about the multi-regional Leslie matrices. And I also want to acknowledge Sunshine Jacobs, who's one of my graduate students who's worked on this project, and Scott Culp, who's a computational scientist at a group called Climate Central, and he did almost all of the physical modeling. So he doesn't do anything related to demography. So climate change and human migration have a really long history together. The earliest reference I could find about climate change and migration dates back to the mid-1970s, where a glaciologist was talking about the West Antarctic, the potential collapse of the West Antarctic ice sheet, and how it could lead to dislocations of coastal cities. And that was the exact term that he used, was dislocations. And so naturally, right, sea level rise tends to dominate this type of literature, where, we sort of like have long cultural histories around, myths and legends of, Atlantis and so on. So we sort of have this like long cultural history around sea level rise and potential flooding and flood myths. And so it's not very surprising that sea level rise tends to dominate this kind of literature. And you can see the kind of language that scholars use when talking about sea level rise. My personal favorite is implicated. And sometimes the language is a bit stronger as well, like will be displaced is very strong language. Most of these kind of studies, though, they tend to model climate migration very broadly. So thinking about, well, New York City is a coastal area, so like what's new is on a coastline, so what's New York City going to do? And other times you end up with something that's a bit more specific. But these types of studies around climate migration have what I think are two really big drawbacks. And the first is related to what we're calling demographic amplification. So if you think about migration processes, they really alter populations in two ways. You have a direct alteration, right, which is like literally one person moving to another location. So you're subtracting one and you're adding one in another location. But that process of migration itself has an indirect effect as well, where now if this migrant was going to have a child in their origin, they might have a child in their destination. They might, because of a gravity effect, you might end up with more people moving to a destination and so on. So we're calling this a demographic amplification. And oftentimes what we just simply do is just look at that direct effect, which is this just general rearranging of people across space without any other consideration for other population processes. And I am very guilty of this in my own work as well. So I'm not just sort of thinking broadly, I'm thinking particularly about my own work. And the second is that oftentimes we focus on these population aggregates. So we're looking at the total number of migrants that could be moving as opposed to demographic characteristics, which I think is just as important. People will be just as interested in than just sort of these like headline total numbers. And in particular, as good demographers, right, we know that the migration propensity really depends upon your age and how old you are. And when thinking about climate migration, the population of the world is expected to age pretty dramatically this century. And so here, this is just right, the classic age schedule of migration, and the dots just relate to the median ages in 2020 and 2021 for the United States. So, you know, barring any other sort of information, there's about a 10 percentage point drop in the probability of migrating, just if we have no other information than age. So if we only focus on totals, we really miss this idea that, you know, what if we end up with you know, population aging and climate change kind of combined, leading to this idea of demographically stuck people, where their background probabilities of migrating are greatly reduced just because of their age. So I think when we put these two together, these two problems, we're really likely to underestimate the demographic implications of climate change. And they're kind of like linked, right? Like, how do you do this demographic amplification if we don't have any age-specific probabilities? We end up, you know, sort of short-sighting or short-changing these effects. So in this paper, we actually address both of these problems. And we focus on a single climatic hazard for simplification, which is just sea level rise, which is where I've done most of my work, and because of its sort of long history. So like I had said at the beginning, there's two components to this. There's one where we have to build a displacement model. So how many people by each age group, we have to get an age-specific displacement model built. And then we have to integrate it within a demographic model as well, which is the second part. So if you look at in my opinion, when you look at the environmental migration literature, there's two really big limitations. One is that it usually relies on case studies of like a single country or a single location or a single environmental event. So in the US, right, like Hurricane Katrina immediately comes to mind. There's tons of work on Hurricane Katrina. And so people will link up like what happened in New Orleans after a major storm struck it and relate it to all sorts of other aspects of environmental change. Or it'll look at, well, people will look at Bangladesh and say, okay, well, what's going on in Bangladesh and how that's going to relate to, say, Brazil, for instance, or some other country. And there are some systematic analyses that do exist, but this case study approach creates this like patchwork of findings, you know, that sometimes they might be in conflict with each other. And the second, again, is this population aggregates, where we end up focusing on the total migrants after these without looking at subpopulations. And when we do have some subpopulations, they're limited again to case studies, and we're back at the first problem. So in this paper, what we do is we'll look at a retrospective or a backwards looking environmental migration as analogs to predict prospective climate migration, so how people might move in the future. And these prospective analyses oftentimes rely on these case studies and so on, or they do some kind of heavy modeling as well, which can be good, but could also be bad. So what we're going to do to begin with and to develop this displacement model is we're going to look for a broader set of environmental factors across subpopulations to try and generate a more generalized migration response to environmental change that we can then use to populate a demographic model. So this is a lot of text for it. The important part is that we're going to couple this statistical outlier technique on about 120,000 county years worth of data in the US to try and find environmental events that are associated with population declines. So we're going to move beyond Hurricane Katrina. Can anybody, I doubt anybody here could name all the major hurricanes that hit the US coastline of the last 40 years, or tornadoes or wildfires and so on. And then once we have this population of, or this sort of set of county years that experience major population declines, we verify that these are actually associated with an environmental hazard, as opposed to like an economic reason, right? Like a manufacturing plant closed or something similar. And then from there, we build a very parsimonious, one-dimensional, age-specific displacement model. So this is the approach, the algorithm. It's implemented in R. It's based on Chen and Liu from 1993. The R package is called TS Outliers. It's really great. It's very easy to implement. And essentially, the way that the algorithm works is it takes a time series and it iteratively fits ARIMA models to it to produce counterfactual time series. And when the residuals are above a significant threshold that you sort of select, in this case, we're looking at a t-score of 4 or greater, it removes that time point and it refits it. And again, searches for new outliers and so on. And this is iterated until no outliers are detected. So what this essentially looks like in practice is something like this. This is a time series of total population for a US county between 1980 and 2020. And I don't think it really takes an algorithm to identify where or really when the event actually occurred for this location, which looks to be in the mid-2000s. This is actually Orleans Parish. And so we can all visually see exactly where when Hurricane Katrina hit this location. And so we could think about, okay, what would this population look like had the intervention not occurred, right, without Hurricane Katrina? And so this is our what it might have looked like, a counterfactual, and this is how the algorithm essentially does it. In this case, this is a t-score of 96, which is absolutely gargantuan. So this is how we're going to do this. We're going to feed in the time series for every county, and we're going to look for large outliers, those that are 4 sigma away between 1980 and 2018. And we're going to isolate negative outliers because we want population declines. We use Sheldis to determine whether or not there was actually an environmental event. And what we did is with this, from this pool, we found 53 county years that had large population declines, but 4 of those were either not in Sheldis, so they didn't have an environmental decline, or they didn't have 50th percentile population losses. And then we have 1 additional county year that had 0 age and sex groups, which we had to exclude. It was a very tiny county in Alaska. So this left us with 48 environmental events over the last 40 years across a very broad range of time periods and sizes. There's tornadoes in there, winter weather, earthquakes, hail damage on crops, and so on. Like it's a very broad brush stroke of environmental events. Okay, so that's the statistical part. Now to get to the demography. So with this, we can use an annual series of population estimates to create cohort change ratios, which are very, very simple and very parsimonious, which essentially means that if you have like 100 5-year-olds in a given time period, 5 years later, we have 125. That gives us a cohort change ratio of 1.25. To make it a predictive model then, right, we can then apply that to a new population in the future, assuming that the cohort change ratios stay constant, that we end up with the same value in the future. So these 48 county periods allow us to relate the change in the total population to the observed change in the cohort change ratios. And we do this, we fit this with a quadratic formula, using the change in the cohort change ratio is equal to a set of values. And this is actually Wilma's flexible mortality model to take infant mortality and generate an entire mortality schedule from it. Only instead of it being infant mortality, which is H in Wilma's model, we're going to be using the change in the population, right? Essentially the percentage change in the population. When we fit the model for each of the age groups, it turns out it works pretty well. This is the percentage change in the population versus the percentage change in the cohort change ratios. Those sort of outliers where they kind of look like linear outliers where there's a lot of population decline, those are counties impacted by Hurricane Katrina. The model fits are pretty well. If you look at the open-ended interval, the slope is it's the least significant slope because it turns out that older people are the least likely to migrate, which is exactly what demographic change tells us, sort of like base demography. These are the R-squareds for all of these different age groups. The model performs really, really well with a couple of exceptions. Men in their 20s and early 30s are kind of hard to predict using this kind of a model, which makes a lot of sense if you sort of think about it. These are the age groups where not only are people leaving for some of these areas, but you get construction workers moving in as well. So you sort of get hard to predict flows. And of course, the open-ended interval as well also becomes very difficult. Older adults are hard to predict. Most of them don't move. There's very little response to it. So from this simple model, then we can make a prediction, right? Which is just taking the cohort change ratio and multiplying it by what comes out. In this case, we're going to drop the intercept, the alpha, the AX value for each age group AX, right? Or the intercept for age group X, because we don't want, if H is 0, essentially, or 1.0, right? There's no change in the population. We don't want to artificially create sort of displacement, essentially. So we drop the intercept. We can then evaluate, okay, well, how well are we able to recreate these populations using this sort of generalized formula? And it turns out it works really well. So this is aggregating all of our cohort change ratios to create a total population, and it works pretty well, I would say. And this is a very broad brush stroke of populations. It works just as well for pretty large counties versus pretty small counties. This is when we aggregate up. And if we look at individual age groups, we also get pretty good results. So, though it's a little bit less, and we get a little bit more smudging that goes on. And if you kind of think about it, it makes a lot of sense that the change in the total population is a product of all the change in all the underlying age groups. So being able to kind of go back and forth from these, right, makes a lot of sense. So this is good. I think this is good for building a predictive model. So performance is good. All we need is this value H, which we have to estimate, which is just the percentage of the population that we would expect to migrate, which makes it very easy to plug into a demographic change model, right? Especially one where we're thinking about climate migration, because then all we really need is to say, okay, well, if a county uses or a population loses 10% of its value, then we can turn it into age-specific displacement values. So that's the first part, which is sort of indirectly estimating or building a model for displacement to go from a retrospective analysis to a prospective model. And then we're going to plug this in to multi-regional Leslie matrices. So to do this, you need 3 matrices. You need a population vector, right, which contains all of our base population information. We need a migration matrix, which contains the probability of moving between locations from I to J. And of course, we need our survival matrix S, which contains all of our combined mortality and fertility information. And with these 3 matrices, we actually build 3 population projections The first one we call base, which is sort of our climate agnostic projection. This is where we take our survival matrix and we multiply it into our population vector to generate a population at time t+1. And we consider this like one where if we didn't know climate change was happening, if it didn't affect any fertility and mortality information, we end up with a population. So if I did a lot of population projections professionally and we never accounted for climate change, this is the kind of model that we would have. The second model is one where we have our migration matrix for time t under sea level rise amount y, right? Because we could have variance in our sea level rise. In this model, the base population is not being integrated in, so we end up with a very comparable number of migrants. This case, we kind of describe this as the migrants are demographically inert, right? We're just moving people across space, but they're not actually integrating into the population value at all. So this gives us a value that's very much akin to all the previous work for comparisons. And lastly, we just go through this amplification process where now the migrants are reintegrated into the population processes so they can have children, they can die, they can attract other migrants, and so on. So these are the three models that were the population models that we built for the projections: a base one, which is a climate agnostic, a displacement one, which is demographically inert, and then an amplification one where all of our migrants actually demographically integrate within the population. So if you need a quick background on Leslie matrices, right, typical Leslie matrix has all this kind of information in it. We just multiply these together. We populate this, right, where we have our fertility across the top, and our subdiagonal contains our survival information. We can do this for multiple populations, in which case we might populate them where our off-diagonal matrices are all just zeros. In this case, we have survival information. The S values in these matrices are cohort change ratios, so they could be above 1. So it's like combining mortality and migration together, and we end up with a future population, right? Like really basic Leslie matrix math for all of this. But in a multi-regional matrix, we can populate those zero diagonals, right? The ones, the off-diagonal matrices with values, which give us the probability of migrating between two different locations. So if we combine our M and our S matrix together, we end up with this new sort of S matrix, maybe multiplied in and so on, just for clarity, just kind of keeping them separate. So what this essentially looks like for doing this work is we populate, right, just like this. We have a value that goes directly into the diagonal, which is, in this case, would be the probability of migrating from I to I, or the probability of non-migrating, right, or not migrating, right? People who are the stayers in a given area. And on our diagonal, we have the probability of migrating from I to J, and then the other one, right, J to I, and so on. And our columns just have to sum to 1, which guarantees that the population that we generate will always equal the value that we end up with a baseline population matrix, right? We have people who are migrating, but they're not being created out of thin air, which might occur if we don't have that diagonal, which contains the probability of non-migration. When we multiply these together, we end up with a new matrix, right? This is the combined matrix between this. If I were to take these two and multiply them into each other, which sometimes, if you read any of the old literature on multi-regional Leslie matrices, I've always found these to be very confusing. They seem like pulling rabbits out of hats. This is generally where they come from, is just by multiplying your M and S together. What we do with this matrix, this M matrix, is we populate it with the results from our displacement model. In this case, for very simplicity purposes, region 1 is losing 10% of its land area. So 10% of the people must migrate. This is just a closed system. You can think about it as just being 2 regions. So they have to go somewhere. They go to the second region. 10% of them do. The reason why we end up with a 0 in the top right corner is because region 2 is unaffected by sea level rise in this case, right? Just for simplicity's sake. So we populate these matrices using 2 primary data sources. For our M matrix, it contains data from the Internal Revenue Service from the US, which publishes this absolutely wonderful data set on county-to-county migration. So if you file your taxes in one county one year and you file them in another county the next year, you're considered a migrant. We account for some variation in this using an ETS model. So that way we end up forecasting forward the migration system. We're not sort of locking it into place. And for our survival matrix, we're using the CDC's estimate of annual series of population estimates to create annual CCRs. And then we're, again, forecasting these forward to generate some level of variability and to allow it so that there's some changes in these cohort change ratios over the long run. If you need a quick primer on sea level rise, this is the most recent projections of how much sea level rise we could have by the end of the century. Sea level rise doesn't end by 2100, and this becomes the H value essentially for our parsimonious model that then goes into and feeds into the M matrix, which ends up with migrants into the future. For this paper, Scott would model essentially only RCP 4.5, which is the mid-run representative concentration pathway for how much climate change we're going to have. 2.6 is the low one. That's like hitting the Paris Accord. 8.0 is like the high one. That's like if everyone's driving F-150s, everyone's got American pickup trucks throughout the world. And RCP 4.5, which is the middle run, essentially has 2 feet of sea level rise, which is about right here. So I'm only pointing this out because we might end up, when I show the results in a second, you'll see that we could be underestimating how much sea level rise is likely to occur, given the very long tail for sea level rise value. Okay, so here's all the demography, it's all in the background. What does this mean? When the rubber hits the road, what does it mean for demographic amplification and comparing the number of migrants when they're integrated in with this kind of crazy statistical model and so on? I'm going to hit you with a very complicated table, and I'm going to walk you through it as well. Because there's been a change in climate policy, or the way you think about climate amounts, we've got representative concentration pathways, and we've got the shared socioeconomic pathways as well. So the RCPs didn't have a population component to them, whereas the shared socioeconomic pathways do. The RCPs follow a very intuitive understanding. 2.6 means low carbon emissions, 8.5 means lots of carbon emissions. In the case of the SSPs, it's not exactly like that. Just know that SSP1 means sustainability. That's our Paris Accord world. SSP2 is actually the mid value. That's the median, not SSP3, which is you'd think it would be if they were actually related to one another. And SSP5 is the high amount. That's where everyone has like lots of carbon emissions. So the sustainability future, SSP1, is incompatible with RCP 8.5, which is a world where everyone is pumping out lots of carbon. So this table has blanks in it, and those blanks are only related to areas where those SSPs are actually infeasible. They're not compatible with one another. I've included here the amount of modeled sea level rise for each of the RCPs. And so they range from a low of about 0.3 meters to about 1.2, which is about 1 feet to about 4 feet of sea level rise. And I've highlighted here SSP2, RCP 4.5, which is the middle value. So under RCP SSP2, we would expect in the United States about 1.5 million climate migrants, people who would be displaced. But so that's just moving people across space, they're demographically inert. But if you actually allow those 1.5 million people to integrate within demographic processes, you end up with about 10 times as many people actually changing locations. So instead of 1.5 million migrants, we could expect about 15 million migrants. To see this graphically, this is all coastal counties. And so that black is the base, that's the climate agnostic projection. The blue is just moving across, right? We're just kind of reshuffling chairs. And then the red is the actual fully integrated demographic processes. And if you take base and subtract displacement, you get 1.5 million. If you take base and subtract amplification, you get 15 million people. The uncertainty is extremely wide in these analyses. And that's owing to two factors. One is we don't know how much sea level rise there's likely to be. And 1 feet to 4 feet in terms of the low end to the high end is drastically different. In the case of Miami, that 3-foot difference is an order of magnitude in the populations that could be affected. And the second major component of uncertainty is how the population itself is going to change into the future. That's also driving this. There's over 100 million person difference in the different SSPs for the United States. But regardless, we essentially end up with 10 times an effect when it comes to the component processes when we actually integrate the demography than if we just sort of move people around. For certain areas, this gets really extreme as well. Here you're looking at Miami-Dade, which is of course Miami, and a location in the North Carolina Outer Banks, Dare County, North Carolina, which is very flat and very vulnerable to sea level rise. It doesn't take a whole lot of sea level rise to have a bait of what I would consider to be a major demographic effect. So in the case of Miami, 2 feet of sea level rise essentially implies about 28,000 migrants, but Miami would see about 250,000 fewer residents by the end of the century. So again, looking at about 10 times. And in the case of Dare County, you're looking at about 8,500 people who would move, but almost 40,000 fewer residents. And if you look at that red curve for Dare County, it starts to flatten out as it starts running out of people who could essentially be displaced. If we look on the flip side, instead of looking at counties or areas that are coastal, if we look at inland areas, we see again the emergence of really major climate destinations. So Rutherford is Nashville, Douglas is Denver, and Washington, Oregon County is Portland, Oregon. And each of these, the amplification is much, much larger than if we just think about just the number of migrants themselves. In the case of Rutherford, they could expect about 35,000 migrants, but that turns into 250,000 additional residents in Rutherford. So for people are already planning for climate migration. They're already thinking through these implications. And if you just look at the number of migrants themselves, we're missing a huge component of the potential future residents in a given area. And again, this is not just because people move and then they have children and so on, but it also changes where the calculus, right? The migration calculus of where people might go. So if somebody experiences a crazy snowstorm in Buffalo, New York, they might decide, Miami seems like a great place, lots of sunshine and palm trees. But because it's going underwater and people are moving away, they might change that migration pattern and move to Nashville instead, right? So we're seeing these indirect effects are actually much larger than the direct effect of the climate migration themselves. This is what it kind of looks like geographically. This is the amplification result for all the counties in the US. Most counties have very small amounts of population change. They're very small, very rural, not a whole lot of people. Other areas can see significant population declines or population increases as well. And just because an area is coastal doesn't mean it's going to lose population either, as you can see in coastal California and in one single location or 2 counties in coastal Florida as well. So when you aggregate these demographic processes, they become very significant. We also know that migration potentially, as I said earlier, follows an age schedule. And we now have this built into the model, right? We actually have how older populations will respond to, we built a model for it. So we can investigate, whether or not we would actually see lower migration in the future for certain areas. And it turns out that when we look at changes in the median age versus changes in the population from our demographic model, we find that in areas that lose more population have older populations than we would expect compared to a climate agnostic future. And that as an area increases the number of people, right? This is the far right of this, we end up with younger populations because who's most likely to move are young adults, and older adults are the least likely to move. So we see this very strong acceleration of population aging and some areas that are very dramatically impacted. And we wouldn't have seen this effect had we not used a demographic model and instead just sort of shuffled people around across space. So this amplification process, we called it demographic amplification because it's kind of like population momentum and it's kind of like a gravity effect, but it's like not exactly like either of those. It's sort of some sort of gray area. And we went back and forth on a whole lot of different terminologies. We were going to call them multipliers, and we were going to call them spillover effects and a whole second order, right? These are sort of like these indirect effects. We called it amplification because it's amplifying these population processes and it's amplifying population aging as well. So this effect is much larger. I was not expecting it to be this large, but it's what we found, that it's upwards of 10% larger. We also find that population aging is I think it's very important, and we wouldn't see this. This is an area that's uncovered by using these demographic models. And if you think about climate migration or displacement sort of broadly, we end up then with this concentrated effect among some of the populations with the least amount of resources. These are older adults who are already, might be on fixed incomes or already strained, and now they're also trying to deal with changes in their environment around them. We know that this is also sort of the evidence broader in the literature that this might be occurring after Hurricane Maria in Puerto Rico. The island aged very rapidly because the people who were likely to move stateside or elsewhere were all young working age adults, which leaves older people behind as well. So it's not just about the climate migration itself and the migration itself, but also who's left behind. What does that mean for those communities? And so we bandied around the term as well, demographically stuck, where we're not really looking at the agency that somebody has, just that those are the age groups where people are unlikely to move. We don't talk about, I didn't talk about this very much, but who's essentially left behind is mostly women, right? Well, women live longer than men. And so we end up with older populations in these extremely precarious coastal environments who are mostly old women who are left behind. So sort of like what's next that we want to move here. So this is just by age and by sex our results are, but we want to add other socio-demographic factors, including race. The US is diversifying. And so thinking about sort of these other demographic characteristics and how they might interplay with this. The Leslie matrices are super computationally efficient. The whole model runs in something like 12 seconds for every county everywhere. Like it's just fantastic. And this H value in this equation means that we could look at other environmental hazards as well. So we could end up with a multi-hazard model. It's just sort of like adding an additional choo-choo, right? Like another train car to it. Another M matrix multiplied in allows us to look at additional climate hazards. So we don't have to just have sea level rise. We can have, for instance, in extreme heat in Arizona and how people might move in response to that as well. So we end up with a multi-hazard model. If I could make one last comment, it's that these kind of formal demographic techniques are super cool and they're super useful. And I think they can tell us a whole lot about the world and where the world is heading. And so I think I'm just super excited to talk about this kind of work. And I want to say thank you. Thank you for allowing me to be here and to present this kind of work.
Great. Thanks so much, Matt. That was really, really interesting. It's a really interesting problem and a super interesting approach as well. And it's been a while since I've seen multi-regional Leslie matrices. So
me too. I would say like nice.
It's nice to see those again in a sort of more modern setting as well. If people have questions, feel free to raise your hand or put them in the chat, and we can call on you. Everyone's being a bit quiet today. I'll start with a question then. I thought the approach of looking at historical outliers and trying to migration events and trying to relate them to environmental events was really neat. I just had a question about you know, these different, and it sounds like you're looking at a whole range of different like climate events, right? And so, but presumably sea level rise is kind of very permanent. So if people migrate out, they can't really migrate back in. Whereas like we know that there's a lot of return migration after a hurricane, for example, or a flood. So I'm just wondering, you know, if you could talk a little bit about, sensitivities to different types of climate events. And I guess there's not really that much data probably on migration due to sea level rise explicitly yet, but maybe in the future, I'm not sure. Maybe in other countries, I don't know.
Yeah, so I think more so because, well, I think I'll back up one step. So more the big worry that I have with this kind of work, my own work as well in this, so it's not just speaking for other people's work, it's not so much the difference in how people might respond to a given climate hazard, but rather the difference between what they call pulse events and press events. So that's like a hurricane or an earthquake or a tornado being a pulse event, right? Like a very rapid onset's the other word people use, versus a slow onset like drought or sea level rise, something that's there where the environment is slowly changing. So thinking about like instead of, or a heat wave versus just the general background, the world is a bit warmer, right? And those, trying to model these slow onset events is very difficult because the calculus that people use for migration becomes very like complicated. People are moving prospectively. They're moving maybe not immediately, but later on. It changes their migration probabilities later in life. People are moving, when there's a bit too much, or they're moving for economic reasons as opposed to like the actual event itself. So trying to disentangle all those and isolate just the effect of like sea level rise, or just the effect of drought, or just the effect of background heat, the fact that it's a hotter climate, is really difficult. Whereas with these pulse events, it's like, well, like it was a Category 5 hurricane, right? Or like it was a tornado. My house got destroyed. I mean, maybe there's some economic background stuff, but like it becomes a prime mover for all of this. So I think. And so we don't have a good handle on these as well. And so oftentimes we end up pointing to these rapid onset events like myself here, partly because of convenience, and partly because of ease as well. Like it's a lot easier to look at these events than to look at these pulse event or the press events, those slow onset, and trying to relate them together. So I am worried about that in this kind of work. And until we have more data on pulse event or on press events, sorry, I'm going to these probably very confusing. On these slow events, I think that this is where I'm gonna be stuck modeling there for a while. And it gets even worse when you think about the general state of migration data and trying to link all this up. It gets even more hairy because most of this is not a multi-year retrospective migration data. We've got 1 year, so it essentially has to be a pulse event until we get better migration data.
Thanks. Thanks. Yeah, I mean, it's such a hard problem, and I think putting some sort of numbers and some range on it is really useful. And you're super clear with your assumptions, I think, which is also really important. Tom, you've got a question?
Yes, I'm thinking that when sea level rises, people would tend to move as short a distance as possible. In fact, there could be some government-sponsored efforts to relocate people as communities almost, to construct new cities that are further inland, but not too far away from the original place. So is that taken into account in some way?
Yeah, in fact, if you look at this map, well, I guess a better question is, what is short distance, right? And so if you kind of like squint your eyes and look at this map, most of the very dark green areas are relatively close to the coastline, most of them, not all of them. And this is only seeing the net change as opposed to the gross change. So in this model, people do move from Miami which is, the bottom part of Florida, to the one county right above it. There are people in this model that do that, or move right from one hazardous coastal area to another hazardous coastal area that's literally a neighboring county. So that's inside of, it's already built into this model for that. I don't sort of put a heavy hand and say, no, sorry, Miami residents, you can't move one county away and still be able to commute to Miami. Like, that's actually completely allowed. It's all free flowing within the model. The managed retreat aspect, I don't model that in here, because if I could predict what the government is going to do, then I probably wouldn't be making this model. I'd be making a lot of money elsewhere on the side. And I'm a little cautious about anybody trying to predict where managed retreat is going to occur. And then on top of that, the cost, which is why I'm very skeptical that managed retreat is going to be a long-term solution for the United States. If you look at just these numbers, so the average cost of managed retreat in the US is about somewhere between $250,000 and $1 million per capita. So per person that has to be moved. And so you're looking at, billions of dollars to move everybody that would be vulnerable to sea level rise. And if not close to $1 trillion. And I just don't see the wherewithal or the budgeting to make that happen.
Thanks.
It's a great question,
though. Vanessa, you're putting stuff in the chat. Do you want to?
Yeah, no, it's just like, I didn't know if I had other questions. We have this privilege because we're chairing the sessions. But yeah, no, I was a bit inspired also by the remark made by Tom. Thinking a bit more macro with demographic theories and things like that. I think one thing also that inspired me from this last conference we had here in Vienna on climate change was how much we're shifting conceptually and the mindset from only thinking in terms of heterogeneities to really looking into climate change as a determinant or as something that really is driving demographic change and not only as a consequence, right? So there's this whole debate. And I was just wondering how much you thought about this and how much you are, especially when you're showing this amplification of population decline or even an aging effect, how could this be placed in the theoretical framework, maybe as another dimension of demographic determinants of aging, or we should start really including going beyond what we currently have in terms of demographic literature and really start including these things, not only as exogenous things happening, but really, really being determinants. And the other thing I was thinking, but of course, it's just to have fun a little, was the boost. Instead of saying amplification, maybe, I don't know, I was thinking if you would sell it, it would be fun. We have the boost model and boosting population change. It just felt like something you could sell, but it's just a remark. Yeah.
Yeah, I like
Thanks a lot for your inspiring talk, really inspiring.
Oh, thank you. Yeah, we literally came up with a list of like 5 different terms and we workshopped them with a lot of people. Boost actually didn't come up, and I kind of like boost. So I like that. I don't necessarily like amplification either. It was the one that we settled on that had the best components that we could, or that the bit, sort of conveyed the idea the best. In terms of thinking about like the other components, so sort of thinking broadly about that, I mean, yeah, here, right, like years ago, Wolfgang had this really nice idea about thinking about population and its effect on the environment, and then the environment's effect on the population. So you could kind of think about this like circular approach. And oftentimes we're only looking at one aspect of that, either population on environment or the environment on population, instead of this sort of like integrated kind of approach. And I'm trying to get more, what I'm really trying to drive to is really think about a much more integrated approach to looking at demographic change. So not just having population and its effect on the environment. So like more people, we get more polluters or whatever, right? In like the very classic sense. And oftentimes when we think about climate change, we're thinking about the environment's effect on population, which is sort of like population displacement and so on. But rather thinking about this sort of like integration a much more holistic approach to it. So aging is one kind of component. I wasn't expecting it at all. In fact, when I ran the numbers, I had to double check to make sure that what I was seeing was not some sort of artifact of the modeling. And it makes a lot of sense to think about. And I don't see this very often at all in the literature more broadly. I started doing a systematic analysis of the climate change and aging literature, and it's shockingly tiny. And I think as demographers, we could really contribute to that understanding, because we already think about the life course, we already think about aging, but what is aging going to look like in a world of global environmental change?
Thank you. Yeah,
great
really
questions.
Cool. I saw a little bit of selectivity. So for instance, depending on the type of like climate adversity that you're looking at, it also affects different ages, right, in different ways. And it's also like in terms of health and mortality, sometimes you don't have like so many expected effects. Like if you have earthquakes, for instance, caused by, of course, earthquakes is a bit less more geological, but sometimes some types of disasters like tsunamis and things like that, of course, the closer you are to the disaster, this affects people who are usually less able to kind of run and to try and seek shelter, sometimes in that regard, but also leaves a scarring effect on the population. So even those that could survive, sometimes they have this. So there are also these effects that happen locally and that impact how people will move around later. So it's really complex. And
yeah, exactly. Yeah, and drought totally does that, right? Like if you experience a drought early in life, it might change your probability of migrating later in life. As you go, I remember that really bad drought when I was a kid, and similar with like a tsunami or something else, or a tornado, or any other major event. It could be a snowstorm.
Yeah, and health of children, right, and mothers, because if you have a drought or you have something that affects like local food agriculture while you're pregnant, maybe this affects the health of newborns. Yeah,
and it could be like here that these second order effects are stronger than we think they might be. Right, just like the direct migration, the direct change because of migration pales in comparison to all the associated population processes that it'll push up against.
Really cool. You have more questions from the audience?
I'll ask another one if no one else. I'm sorry, I think I missed. How far are you projecting? How many years?
2100.
So okay, and so your projection of the cohort change ratios is a REMA. So are they assumed to be stationary?
No, not quite, but yet close to stationary.
Okay, cool. And then, so with the projections, is there any constraint on like the total population? Because those, I don't know much about the shared social pathways, but are they the version that they've got the population projections in them? Is that?
Yeah, the SSPs have population projections. So these are controlled to those.
Oh, okay.
To make them kind of, well, they're a really nice thing to control to, since they are produced by age and by sex. It's already used inside the different climate scenarios, so that they're very, very convenient. But no, I don't have a growth limit on any of these counties. Most of the counties don't approach sort of like a ceiling of what you would consider a theoretical ceiling for them, without some kind of a land use model associated for build out within the U.S.
Yeah.
Which I don't have a model for that.
Cool. I was just curious.
Yeah, that comes up a lot, and I had to double check to make sure we weren't near like approaching a sort of like a ceiling for many of these areas.
Cool. Cool. Well, unless anyone else has any more questions, last chance. I'd just like to thank Matt again for a great talk. And as Vanessa said, really inspiring, thinking about issues that I haven't really thought about before, and I really enjoyed it. A really complex but really important topic. And a great use of classical formal demographic projection models in a new context. So thanks very much for coming, and thanks everyone for joining us. We'll be in touch soon about the next meeting.
Thanks for having me. Thanks, everybody. See everybody at PAA, hopefully.
Yeah.
Yeah. Thanks, Tom. It was great.
Thanks.